Okay, so let's recap what we did yesterday about resistors in series. So we said to see if a circuit is in series, you need to look at the light bulbs or the resistors that are not branched and just ignore the voltmeters. And then we said to calculate the total resistance in series, you just have to add all the resistors together. So the formula is Rs is equals to R1 plus R2 plus R3, etc. And the more resistors you add in series, the greater the total resistance will be. Then we said the current in series is the same everywhere, which is also equal to the total current. But we said that voltage in series is divided, and if you add all of the voltage, you will get the total voltage. And since it is divided, you can use this formula here to calculate the voltage of each specific resistor in series. Right, so now that we know the theory, let us move on to examples to see how it actually works in series. So we're going to page 133 of your textbook, and this is just an experiment they done to see how the voltage and current is affected in series. So if you're looking here at this circuit, can you see that you have a circuit and then you have branches? But all of these branches that you have here are for the voltmeters. And we said that voltmeters are always connected in parallel. So if you want to see if a circuit is in series or parallel, you will ignore the voltmeters. So we are going to ignore all the voltmeters. What we're going to look at is the light bulbs. And can you see you have two light bulbs, bulb 1 and bulb 2. Both of them are not in branches, they are next to each other, which means that this circuit is a series circuit. Now if we go here where they actually showed us values, we can see here we have a voltmeter over the battery or the cell, and this voltmeter reads 3 volts. Now we said the voltmeter that is across the cell or battery will always give you the total voltage. So it means that in this circuit here, the total voltage is 3 volts. And we also said that in a series circuit, voltage is divided, and if you add all of the voltages, you get the total voltage. Now if you look at bulb 1 and bulb 2, can you see each one has a voltage of 1.5 volts and 1.5 volts, which means this 3 volts here was divided between these two light bulbs. So each one got 1.5 and 1.5 volts each. And in this case, it was divided equally. Now, it's not going to always be divided equally, but in this example, it is. And if you add 1.5 volts to 1.5 volts, that will give you the total voltage, which is 3 volts. And then, since it's a series circuit, we said that the current is the same everywhere, which is equal to the total current. And can you see that we have 3 emitters in this circuit? We have this emitter, we have this one, and we have this one. And can you see that they all give us the same reading? This one is 0.5 amps, this is 0.5 amps, this is 0.5 amps. So they all give us the same exact reading because in series the current is the same everywhere, and it's also equal to the total current, which means the total current is also 0.5 amps. Right, let's look at example 6 on page 134. Now, example 6 is just some kind of theory that you need to know. Now, remember we said that emitters are always connected in series and voltmeters are always connected in parallel. Now, if you look at this circuit, can you see here, they actually put the voltmeter in series, so there's no branch, and they put the emitter in parallel, so they swapped it. They did the opposite of what's supposed to have done. Now, if you do something like this here, it will actually be that the emitter will not give any reading. So the reading on the emitter will be 0 because emitters cannot work in parallel, they only work in series. But the voltmeter, if you put it in series, even though it's supposed to be in parallel, it will give you a reading still. But the reading won't be the voltmeter, the reading will be the EMF of the battery. And remember EMF of the battery, we said it's the voltage when there is no current flowing. So whatever the voltage of the battery is, that will be the reading that you'll get in this voltmeter, which is connected in series. Now don't worry too much about this example. I'm just showing you so you know what to expect if you see something like this. Right, let's move on to example 7. Now this is the important parts because this is where you're going to do calculations to put everything you've done and applied it in an actual calculation. Right, so example 7, it says 3 resistors, 5 ohms, 10 ohms and 35 ohms respectively are connected in series to a 100 volt source. Now since the resistors are in series, it means that this is going to be a series circuit. Right, number 1, sketch the circuit. Now can you see they sketched the circuit here? It's a series circuit, so there's no voltage, there's no branches. And they have the 3 resistors, R1, R2 and R3, and then they have the battery there, which is 100 volts. Right, then number 2, calculate the equivalent, effective or total resistance of the circuit. Now remember we said equivalent, effective or total all means the same thing. They all mean the total resistance of the circuit. So in a series circuit we said to calculate total resistance you will just use this formula, which is Rs is equals to R1 plus R2 plus R3 etc. And since there's only 3 resistors here, you will say R1 plus R2 plus R3, which in this case is 5 ohms plus 10 ohms plus 35 ohms, and that will give you 50 ohms in total. And remember, all answers must have a unit, and the unit for resistance is ohms. Right, number 3. Calculate the current that flows through the circuit. Now they're asking us to calculate current, and we know that in a series circuit the current is the same everywhere, so it doesn't matter which current they're asking us to work out, it will be the same, and it will also be equal to the total current. So since they're asking us to work out current, and current in series is the total current, it means that when we work out current we have to use the total voltage of the cell and the total resistance. So if they're asking you to work out total current, then you need to use total voltage and total resistance. Okay, if they're asking you to work out a specific current, then you will use a specific voltage and a specific current. So remember, if they want total, you use total for everything. If they want a specific thing, use specific thing for everything. Right, so it's a series circuit, which means it's total current. So you're going to use the formula, which is the resistance formula, and make I the subject of the formula. So I is equals to V over R. And since it's total, we're going to use total voltage and the total resistance. And the total voltage is the one of the battery, which is 100 volts, and the total resistance in series we just worked out in question 2, which is 50 ohms. So 100 divided by 50 will give you 2 amps. Right, let's move on to number 4. The potential difference across each resistance by applying the definition of resistance. Now when they ask us to apply the definition of resistance, they basically telling you to work out resistance using the resistance formula, which is R is equals to V over I, or if you put it in this way, it will be V is equals to IR. Okay, so it's the resistance formula. So they're asking us to work out the potential difference of each resistor using this formula here. And remember we said voltage is divided in series, and each resistor will get a different amount of voltage, and we can't just say that each one will get an equal amount because they might not get an equal amount. So we're going to use this formula and work out how much voltage each of these resistors have. Right, so let's start with the 5 ohms one. So you're going to say V is equals to IR, and then current is the total current, because we said in series current is the same everywhere, so each of these resistors will have the same current, which is what we worked out in question 3, which is 2 amps. So current is 2 amps, and then the resistance in the 5 ohms one is 5 ohms, so you will multiply it by 5 ohms. Now can you see that we are using 5 ohms as the resistance? We are not using the total resistance, which is 50, because here they're asking us for the voltage, and each voltmeter or each voltage in each resistor will give you different voltages. So it's not the total voltage, it's a specific voltage, therefore we use specific resistance, not total resistance. Right, so it will be 2 times 5, which will give you 10 volts. Then for the second one is the 10 ohms one. So again, you're going to use the same formula, V is equals to IR. The current will still be the same, 2 amps, because it's a series circuit. And now for the specific resistance, it will be 10 ohms, because we're dealing with R2, which is 10 ohms. And that will give you 20 volts. Then we'll move on to the last resistor, which is R3 with 35 ohms. Again, you use the same formula. Current is still the same because it's series, so it will be 2 amps. And then resistance, it's specific resistance, so you're going to use the specific one, which is 35 ohms, and you'll get 70 volts. Now, can you see that you have 3 resistors, R1, R2, and R3, and each of them have a different voltage. The one that is 5 ohms has 10 volts, the 10 ohms one have 20 volts, and the 35 one has 70 volts. Each of them have a different voltage, which just shows that in a series circuit, even though voltage is divided, it is not divided equally. It depends, and you actually have to calculate what the voltage is in each resistor. Okay, and just remember, when you're working out the voltage of each resistor is different, so you cannot use the total resistance. You have to use the resistance of that specific resistor. Okay, right, let's move on to number 5. It says the potential difference across each resistor by using the relationships in the circuit. So again, they're asking us for potential difference of each resistor, but now they're saying we must use the relationships and not the definition. So what they mean by that is to use the potential divider formula, which if you go back to your notes, you will see it is this formula here with the x's. Right, so they're saying you must use now this formula to work it out. Now I'm just going to show you one example because it's basically the same thing. So you're going to use this formula. So Vx is equals to Rx over Rs times V total. Now when it comes to Rx, they mean specific. Remember I said X means something which is specific. So because Rx is specifically dealing with a specific resistor, in this case it's R1, which is 5 ohms, you're going to put the resistance of that 5 ohms. And then Rs, where you see a subscript S, that means resistor in series, which is the total resistance in series, and that will give you 50 ohms. Right, and then you multiply that by the total voltage, which is the one across the cell or battery, which in this case is 100, and that will give you 10 volts. Now, if you look at question 4 and question 5, you will get the same answers for each thing. It's just that you're using different methods of getting these answers. And anytime you're using electric circuits or you're doing any calculations on electric circuits, you can do the answers in many ways, but you'll still end up with the same answer if your reasoning is correct. Right, and if you look at the 10 ohms one, can you see you get 20 volts, which is the same as if you worked it out with this formula. And the 35 ohms, you get 70 volts, which is the same as this one. Right, let's go on to number 6. It says here, calculate the amount of charge that flows through the 35 ohm resistor in 2 minutes. Now they're asking us for charge and they're giving us time. And the formula that has charge and time together is this one here, which is the current formula. Q is equals to I times change in time. Then the current, we know it from question 3, which is 2 amps. The time, remember we said time is always in seconds. And here they gave it to you in minutes. So you need to convert it to seconds. So it's 2 minutes times 60 seconds, and that will give you 240 coulombs. Right, and then the last one, question 7, the amount of energy that is converted into heat and light by the 35 ohm resistor in 2 minutes. Now they're asking us for energy, and the only formula that has energy in electric circuits is the one with voltage, which is W is equals to V times Q. Right, so now we have to just substitute V and Q, but can you see that they're asking us for the energy in the 35 ohm resistor, which means we cannot use the voltage that is the total voltage. We need to use the voltage that goes through the 35 ohm resistor, which is this one here, R3. And if you go to question 4 or question 5, you'll see that the voltage of the 35 ohm resistor is 70 volts. So we need to use 70 volts and not 100 volts because that's the total voltage. Right, so for voltage, we're going to substitute 70 volts. For charge, we're going to substitute 240 coulombs, which we got from question 6, and that will give you 16,800 joules. Okay, let's go on to the last example, which is example 8 on page 134. Right, it says 2 cells are connected in series with 2 resistors R1 and R2 together with an emitter and a switch. A voltmeter is also connected across R1. The voltmeter reading is 4 volts and the emitter reading is 1.5 amps. The resistance of R2 is 3 ohms. Right, number 1, draw the circuit diagram. So remember, it's a series circuit. So you're going to have a series circuit, and they said R1 and R2 are next to each other in series. And then they said the voltmeter across R1 is 4 volts. Now, every time you draw a voltmeter, even if it is a series circuit, you have to draw the voltmeter in a branch, because voltmeters are always in parallel, even if it's a series circuit. So even though this is a series circuit, the voltmeter is in parallel. And then they said the emitter is 1.5 amps, because remember, an emitter you can put it anywhere in series, because in series it will be the same everywhere. So it doesn't matter where you put it in series, it will give you 1.5 amps. Okay, let's go on to the calculations. Number 2, calculate the resistance of R1. Now, if you look at R1, can you see the voltmeter across R1 is giving a reading of 4 volts. So, the reading of this voltage of R1 is specifically 4 volts. Now, 4 volts is not the total voltage because this is only across R1, and remember voltage in series is divided, so R1 and R2 will give you different readings. Right, so they want the voltage of R1, and we're going to see what information we have. Now we know it's a series circuit, which means current is the same everywhere. So the current, which is 1.5 amps, will also be the same current for R1. So we have current, we also have voltage, which means we can use the resistance formula, which is R is equals to V over I, and then just substitute. So the voltage specifically for R1 is 4 volts, so you're going to substitute 4 volts. The current is the same everywhere, so it will be 1.5 amps, and that will give you a reading for R1 to be 2.67 ohms. Right, let's go on to number 3. The potential difference across R2. Now they're asking us for potential difference, which is voltage across R2, right? So they're asking us for this voltage here. Now we know voltage is divided, and it's not necessarily divided equally. So we can't take this voltage and say it's the same. It's not going to be the same. So again, we have to see what information we have. We said we have current because current in series is the same everywhere. So it will also be 1.5 amps for R2. We have the resistance for R2. So now we can just use the resistance formula and work out voltage. So again, you're going to say V is equals to IR. Current is 1.5 amps still because it's the same. The resistance for R2 is 3 ohms, and that will give you voltage for R2 4.5 volts. Now can you see how different it is? R1 has voltage of 4 volts, but R2 has 4.5 volts. That just shows that in series voltage is divided, but it may not necessarily be divided equally. Right. Then number 4, they're saying calculate the EMF of each cell. Now remember, if you have cells, many cells make a battery, and if you add the voltages of each cell, you will get the voltage of the entire battery. Now the battery's voltage is the total voltage, but we don't have the total voltage, but we can definitely get the total voltage, which is actually the EMF. So they're basically just asking us to work out total voltage. Now remember, we said in a series circuit, voltage is divided, and if you add all of the voltages, you will get total voltage. So if we add the voltage of R1 and R2, that will give us total voltage. And R1's voltage, we have it, it's 4 volts. R2, we calculated it, which is 4.5 volts. So if you add the 2, which is 8.5 volts, that will give you the total voltage of the battery. Right, now the question says you want the voltage or the EMF of each cell, which means not the entire battery, you want it for each cell separately. Now in this picture, can you see that there is 2 cells, which means you need to take this voltage and divide it by however many cells there are, which in this case is 2. So you're going to say 8.5 volts divided by 2, which is 4.25 volts. So this tells you that each cell has a voltage of 4.25 volts. Right, let's go to the next question. Number 5, calculate the amount of heat released through the 3 ohm resistor in 2.5 minutes. Now, they're asking us for the amount of heat released. Heat, remember, is energy. None of the formulas we have includes heat, but heat is a form of energy, which means they're just asking us for energy. And we know that there's only one formula that has energy, which is this one. W is equals to VQ. Now for this formula, we need to have voltage and we need to have charge. But we don't have the charge. We do have the voltage, but we don't have charge, which means we need to calculate charge first before we can use this formula. And they have told us that we want the 3 ohm resistor energy in 2.5 minutes, which means that they gave us time. Now, if you wrote down all of the formulas that you have, and you can see that if you use this formula, Q is equals to IT, you can substitute I and T, and then you can calculate Q. From Q, you can put it into this formula with the voltage and then calculate the work or the heat energy. So sometimes you won't be able to calculate something in one step. You need to do it in maybe 2 or even 3 steps. So what you need to do is, On a page, write down all the formulas that you have, and then write down all the information you have. And then if you can't use a formula directly to get an answer, maybe you have to use one formula first, get an answer from the first formula, then put it into the second formula, and then get the right answer. So that's what we have to do for number 5. So for number 5, we first have to work out charge. So charge is equals to I times change in time. So current is 1.5 amps. Remember, we said it's series, so it's the same everywhere. Time, they gave it to us. They said it's 2.5 minutes. So remember, we cannot use minutes. We have to change it to seconds. And that means you have to times it by 60. So it will be 2.5 times 60. And that will give you 180 coulombs. Now, we need coulombs only because we need to use this formula to work out the energy. So this coulombs, what we worked out now, 180 coulombs, we're going to substitute it into this formula. So we're going to use the formula W is equals to VQ. Voltage is 4.5 volts. Now remember, the question said the amount of heat released through the 3 ohm resistor. So the 3 ohm resistor is R2. So they're asking us to use it for R2, which means we need to use the voltage specifically for R2, which in this case we worked out in question 3 to be 4.5 volts. So you cannot just use any voltage. You need to use the one that they're telling you to use, which is the specific one in this case for R2. So you're going to say 4.5 times the 180 coulombs from here, and that will give you 810 joules.